If you had to build a skyscraper, you wouldn't pick this one. Just look at the hurdles. Typhoon winds to withstand, a rigid deadline to meet, and a towering goal no skyscraper has ever reached: generate all its own power.
This is the holy grail for mechanical engineers.
At the southern tip of China, beside the Pearl River, rises the city of Guangzhou. 1,000 years ago, it was an international hub, a key port on the maritime Silk Road that linked east and west. Now the world is coming back. Guangzhou is hosting the next Asian Games. As the big event looms, the city is getting a multi-billion-dollar makeover. Dozens of buildings are going up in Guangzhou's new central business district, but none like the Pearl River Tower. When complete, it will stand 71 stories high, among the world's tallest buildings. It will use 60% less energy than a normal building its size, and it will harvest sun and wind to make energy of its own. Nature is both ally and enemy here. Typhoons pound southern China each summer like clockwork. A major fault line for earthquakes runs near Guangzhou itself. Engineers have to erect a building that not only harnesses the forces of nature, but withstands them. Right now, 1,000 men are racing to keep construction on schedule. Across the site, Chief Engineer Dr. Cui Xiaoxiang is turning a radical blueprint into a concrete reality.
我的心理压力确实非常之大的。
My pressure is enormous. Frankly, my hair turned white after I came here. My biggest worries in the job are about safety and quality.
On floor 45, they're installing 8-ton steel beams. They assemble the entire building using thousands of high-strength nuts and bolts instead of welds, the better to withstand earthquakes.
The problem that comes with using only nuts and bolts is that we have to ensure high precision. With welding joints, you still have room for compensation. But when we use only nuts and bolts, we need to contain the deviation within a few millimeters. Otherwise, the whole steel structure will have huge errors.
Precision installation on site is mirrored by precision manufacture here, the Huning Steel Factory in Jiangsu Province. The factory will produce over 18,000 steel pieces that make up the Pearl River Tower. Over 2 years, this factory will manufacture 29,000 tons of steel, enough to build almost 3 Eiffel Towers. Before they mass produce the parts, they stress each prototype to breaking point. A computer records the force applied and the relative strength of the steel. All the steel must be perfectly flattened before they can start making components. They curve large beams by applying precise amounts of pressure at specific points along the length of the beam. They check every weld for defects using ultrasound. In total, they will drill 820,000 bolt holes to complete the structure of this tower. This machine can drill holes in 5 connection plates simultaneously, while maintaining accuracy in every plate. Some of the faceplates have more than 650 separate bolt holes. The factory prefabricates key structures for the tower to avoid setbacks on site.
Because pre-assembly can reveal the quality and precision of each part. If everything matches, then we ship to site. If not, we correct the errors at the factory to make sure everything goes smoothly on site.
Today, the words construction and China go hand in hand. Each year, the nation adds 2 billion square meters of construction, half of the world's new buildings. But this client wants a building that stands out from the rest. In summer 2005, they issue a competition brief to the world's leading architecture firms. Architect Adrian Smith has created such icons as the Jinmao Tower in Shanghai, once the tallest building in China, and the Burj Khalifa in Dubai, now the tallest building in the world. So what do you do for an encore?
When I first started reading the brief, and they talked about a building for the future, and they talked about a building that harmonizes with the environment, I thought that here is a client who we could propose a zero-energy building to.
A super tall building that produces as much energy as it consumes. No one's ever built such a building. It's a radical design, based on a concept you don't usually associate with architecture: high performance. Adrian Smith and colleague Gordon Gill have been eagerly awaiting an opportunity to put their theories on high-performance building into practice.
Using aerodynamics and looking at the design of automobiles or the design of jets really helps you to understand how things perform at very high levels.
It's really designed to perform like an athlete is shaped, his muscles are shaped for performance.
We're going to try and funnel that wind through a port or a fuselage of some kind, and maybe we can mold the body like a jet, like a fuselage on a jet, or a car, like a Ferrari. My instinct was to, almost like a catcher's mitt, you know, just to catch the wind and see if we could use it to our greatest advantage.
Just 1 week later, Gordon draws what will become the most energy-efficient super tall building in the world.
I knew that there was something here that was different. I knew it, and it just poured out, and it was great. It was a great morning, and I'll never forget it.
He sketches the future, a building that curves like a sail in the wind. 4 holes will house integrated wind turbines to generate power. A unique double skin of high-tech glass covers the whole building, with inbuilt solar panels to generate even more power.
And when I showed the final one to Adrian, I think he said, it looks like a car seat. and I said, yeah, it kind of does.
The client in China loves the concept.
The thing that grabbed me the most was the zero energy idea.
It's the key that gets them the contract. 4 years on, the radical design is becoming reality. Engineer Roger Frechette flies in for regular visits to check progress.
The project got off to a rather slow start, but the further above ground the building grows, the faster the speed of construction. And I think the more they learn about the building, the faster things go. And right now they're adding 1 floor every 3 or 4 days. Now this is very exciting. You can begin to see the installation of the steel that is curving back towards the building. And this is really the beginning of the bottom of that upper row of wind turbine openings. So you can start to see the shape of the building come together.
What you don't see is what it took to get this far. Beneath is a vast basement with a footprint roughly 3 times larger than the one on the surface. And at 30 meters deep, one of the deepest basements in China, able to house 800 vehicles.
We faced a lot of difficulties in the construction of the basement.
Just 10 meters down, they hit bedrock. They use explosives and pneumatic drills to hollow out the basement in stages, removing enough rock and earth to fill nearly 100 Olympic swimming pools. To support the tower, they set 4 steel mega columns with smaller columns in between, all sunk 30 meters below ground. Inside this steel skeleton rises the concrete core, the spearhead of the whole construction. The outer steel skeleton is complete to floor 46, and the concrete core has just reached floor 53. On top of the core, they're installing the beams that make up the core wall. This corner beam is headed for the work platform on floor 53. "230 meters above the ground, the crane driver is totally reliant on instructions from his teammates on the work platform below. With careful coordination, they guide this monolith into place. The crane holds the beam steady while workers position it within a tolerance of just 2 millimeters. A survey team calibrates the final adjustments. Once it's set, somebody has to release the beam from the crane. It's not a job for the faint-hearted. But this old hand even has time for a break at the top. Positioning steel on Pearl River makes conventional high-rise work look like a cakewalk. The reason is all those gorgeous curves.
The multiple curves require us to think of the building's surface in 3D terms, instead of as a flat surface, like most conventional buildings.
They use a complex system known as double-layer surveying that requires many more points to position each piece. First, they set up survey points high up on neighboring buildings. Then they establish another set of points on the tower's perimeter and on the edges of the core, so they can measure the exact height of every piece they install. The double-layer system is rarely used on conventional buildings, but engineers here can't live without it. But positioning the steel is only the first challenge. The next, getting concrete up to the steel without using scaffolding. On the Pearl River Tower, 2 shifts are working 10 hours a day to construct the mega columns. Work moves twice as fast here, thanks to a clever device known as the hydraulic climbing frame. There's a climbing frame attached to each of the 4 mega columns. This frame allows concrete to be poured for each mega column without the need for scaffolding from the ground up. Gu Jiangcai is in charge of the climbing frame, which is patented by the Shanghai Construction Group.
Now we use the climbing frame as the scaffold, moving upwards all the way. It's very advanced.
The climbing frame consists of a vertical track, a mold to hold the concrete, and a work platform on top. The frame moves up with the mega columns as the construction climbs higher. On floor 26, they've just installed reinforcing rods around the steel core of the mega column prior to pouring the concrete. Once all gaps are corrected, the mold begins moving up from the floor below.
Using this technology with a one-time investment, we can simplify the operation, save time, and reduce the workload on the crane.
It takes 2 hours to elevate the mold from floor 25 to floor 26. Then the team fixes temporary steel beams to reinforce the mold before they pour the concrete. Engineer Zhang Sung inspects each stage.
We normally finish one level every 3 days. If we didn't use the hydraulic climbing frame, we'd need 6 days for each level.
But now they face another towering challenge: getting concrete from ground level to 100 meters high. This state-of-the-art Sani concrete pump shoots the concrete up to floor 27 at the rate of 30 cubic meters per hour, enough to fill a shipping container. Like arteries in a body, a network of pipes connects every floor in the building. From floor 27, they fill the mold on floor 26. When the concrete dries, the cycle begins all over again. 26 floors done, another 45 to go. The high-performing Pearl River Tower will use 60% less energy than a conventional building its size. A key high-performance feature is the double-skin glass facade.
The way to think about this is like a sponge. The building will have a breathable skin. It will use its envelope to regulate not only how much light comes in the building, but the temperature and the amount of radiation that is allowed to penetrate into the building.
The Pearl River Tower will boast the largest double-wall facade in the world. Designing it poses a huge challenge for designers at Skidmore's and local architects, the Guangzhou Design Institute. The Pearl River Tower is the baby of senior architect Huang Huijing.
In the design phase, we had a lot of questions. Like, will the temperature be a problem for the double-skin facade?
Such facades work. Europe has used them for years. But no one has ever used this technology in a hot and humid environment like southern China.
Fantastic view.
Traditional European double-skin facades keep heat in. In Guangzhou, they need a design that keeps heat out. Double skins contain 2 layers of glass with a cavity in between. Traditionally, the inner layer is made of low emissivity or low E glass to keep heat from escaping. The wrong design for tropical Guangzhou. The Pearl River Tower takes the same components and turns them inside out. Because the average temperature in Guangzhou is 22 degrees Celsius, designers move the low E coated glass to the outside, deflecting much of the sun spectrum away from the building. And automated silver blinds inside the cavity will also help block out heat. Together, the double facade and automated blind system will block out more than 70% of Guangzhou's heat. Sensors on the outside of the building will monitor the sunlight and adjust the blinds automatically. Lighting accounts for up to 1/3 of a building's energy bill. But here, architects have made ingenious savings. Beams suspended across the ceiling will conceal energy-efficient light bulbs. The curved ceiling panels will reflect this light, along with daylight, onto the work area below.
So we ended up with a series of vaults in the ceiling, and it keeps the light even. And when you do that, you can space them farther apart. I think we got about 30% less fixtures in this building with the same level of light, and that was huge.
The next challenge, how to keep people cool but save on energy.
Most buildings use air to air condition people. Large quantities of cooler air come in and they come in contact with the human body and make you feel cooler. This building does not do that.
Instead, engineers control the temperature by running chilled water through metal ceiling panels, a technology called chilled radiant ceilings.
So the entire ceiling system in the building becomes a cold radiator.
So when people walk into a room, the heat from their warm bodies exchanges with the cool of the ceilings, keeping them comfortable. But the solution creates its own problem in hot and humid Guangzhou.
Well, the main danger is that you get water dripping all over the place. I know it's like a rain. If you have humid air coming into the building, that humidity would collect on the ceilings and would condense and start dripping all over the offices.
Senior architect Huang Huijing tackles the solution.
When using new technologies for the first time, relying on computer simulation is not enough. We need to do physical testing to be on the safe side.
On the 9th floor, they mock up 3 rooms to test the ceiling and facade together. Each room uses the same technologies, but from different manufacturers, so designers can choose the best products for the building. Engineer Roger Frechette and architect Huang Huijing check the results.
That looks very good. Beautiful sunny day too.
Yeah, we have tested one time and the result is very good. There's no water in the surface.
No condensation at all. Well, that's fantastic.
The radiant ceilings will work so well, the building won't need a full-size, energy-guzzling air conditioning system.
Now, because we only need air for the ventilation, for the breathing purposes, the amount of air we need is significantly less, roughly 25% of what you would need for a typical building design.
But another challenge looms, one that threatens the very health of the tower's occupants: contaminated air. Normal air systems circulate the same air around a building up to 5 or 6 times.
A lot of people get sick in a building from the air handling systems, from other people down the hall that may also be sick.
In Guangzhou, the danger of airborne disease hits close to home. In 2002, this province was ground zero for a deadly pandemic known as SARS. Before the outbreak was contained, 1 victim in 10 died. But the Pearl River Tower uses air only once, creating a much healthier building.
Having a healthy environment was something that was absolutely critical.
Pearl River's fresh air is circulated through the building via vents in the floor. Because air is naturally buoyant, it rises through the breathing zone.
Most buildings, air comes in from over your head, and you need fans to push the air down, and those fans pushing air down takes energy. So again, air coming into the floor saves energy.
After implementing our solution, we estimate we'll make energy savings of 40% in this one area.
And this radical design yields another benefit. Because they'll need so little mechanical equipment, they'll need much less ducting between floors, a saving of 300 millimeters per floor. Throughout the building, they gain 5 extra floors, just over 9,000 square meters of rentable office space.
So when you look at the economics of the building, that additional rent that can be collected goes a long way to help pay for whatever premium might be involved with doing this high-performance building.
In fact, they estimate the Pearl River Tower will recoup its construction costs in just under 5 years.
Now we can say that sustainable buildings do not necessarily have to cost more. And this is a very important point, I think, in terms of the understanding of sustainable buildings.
So even if you are not interested in green or sustainability, but you are interested in money, you may think that this was the right way to go.
Now it's time to put all that theory into practice. The devil, as always, is in the detail. Designers must nut out every element before manufacturing can begin. The Zhenghe Curtain Wall Company faces the ordeal of designing, manufacturing, and installing the largest double-skin curtain wall in the world. A team of 30 designers will work for 18 months on this one project. Using 3D computer software, they'll design every single feature that makes up the curtain wall. The complex curves on Pearl River test the team like never before.
Because of its complex shape, there's a great variety of facade units. So the difficulty in manufacturing increases tenfold.
The tower has 7 types of windows and 6,000 panels in total. On the factory floor, 3 production lines and 300 employees work solely on Pearl River. 1,900 tons of aluminium will go into making the window frames for the Pearl River Tower. This will be the largest window curtain of its kind. The panels are some of the biggest ever seen. The largest, at 24 square meters, is more than 3 times the size of a panel on a conventional high-rise. In all, Pearl River will be cloaked in 80,000 square meters of low-E glass, enough to cover 10 soccer fields. But all that glass opens a window for trouble. Water, one of any building's worst enemies. Southern China gets up to 12 typhoons each year. April brings the monsoon season to Guangdong province. For half the year, more than 150 millimeters of rain falls on Guangzhou every month.
We have to ensure that the curved surface is watertight, both inside and out.
With its reputation at stake, Zhonghe undertakes its own testing of the window curtain at the Canton Quality Control Station in Guangzhou City. This giant section of window curtain will endure more intense wind and rain over the next 2 days than the building might expect in its entire lifetime. Architect Russell Gilchrist of Skidmore's and local architect Huang Huijing will observe the testing firsthand. In the wind test, pressure sensors placed inside the facade will measure the distortion of the glass. A large pump inside the glass cavity simulates high winds by sucking in air, causing a buildup of negative pressure. The facade is battered by winds 1.5 times higher than the worst winds ever recorded in Guangzhou. Wind pressure can open gaps for water. So does the glass remain watertight? Turn on the Typhoon.
All facade projects in this country are subject to this kind of test. But since it's the first time a double facade is being used in this climate, this test is a first in our region.
The interesting bit will be when they turn on the fan, because that will actually simulate horizontal wind and rain together. And that's where we test all the little gaskets to make sure that everything is watertight.
The fan simulates winds of 144 kilometers per hour. Outside the facade, technicians check for damage on the rubber gaskets. And on the inside, Russell is delighted to find it's bone dry.
I think we're good. That's a good test. If you get weather like this, that was a good test for it to pass. Yeah.
Good thing rain can't get in, because the architects have set the tower directly into the prevailing winds to harness their power. Facing Pearl River directly into the wind is a bold move.
Now, that's a little counterintuitive, because in a super tall building, you're trying to reduce the wind load on the building. And most people would tell you that it is unwise to face the broad face of the building directly into the wind, because the sail effect on that building is tremendous.
The prevailing wind that comes from the south 10 months of the year will hit the tower head-on. The wind will funnel through 4 wind holes, located 1/3 and 2/3 of the way up the building. Dr. Sui and colleague Mr. Wang check out the bottom 2 wind holes.
Do you feel the wind on this side? Once the glass facade is in place, the wind power will be greatly enhanced. There'll be an aerodynamic tunnel.
Wind tunnel testing undertaken in Canada reveals the wind speed through the holes will accelerate up to 2.5 times.
I think most people would understand that if you narrow down a funnel, it's going to accelerate whatever you're putting through it, especially if it's symmetrically shaped. But I didn't know it was going to be 2.5 times.
Their next challenge, finding wind turbines that are up to the job. Wind turbines like these are sprouting across the globe, but they can only cope with wind from a single direction and won't work in a turbulent cityscape where gusts of wind can come from all sides. The answer? Vertical turbines. They spin no matter the direction of the wind. Best of all, they cope with the turbulence common in the city.
In other buildings, the wind turbines are commonly placed at the top or on an open platform.
But in a radical move, Pearl River's turbines are the first in the world to be integrated within a building, with each of the 4 wind holes housing 1 vertical turbine. It's revolutionary thinking, but it rattles the engineers' nerves.
People are concerned that vibration will be a problem when the turbines start working here.
The noise and vibration could do more than annoy the occupants. If the vibration mirrors the natural frequency of the floors, then the effect will be amplified, causing structural damage. The architects decide to commission a test at Hunan University, known for its elite engineering department. Engineers use a 1:150 scale model of the tower, complete with its own mini turbines. Inside the wind tunnel, they subject Pearl River to high winds, measuring wind pressure across the entire surface of the tower. Taking their wind pressure readings, they calculate the vibration of the wind turbines and compare it to the natural frequency of the floors. They conclude that the vibration of the turbines will not vibrate the surrounding floors. For the engineers, no vibration means good vibrations. Not only will the tower harness the wind to make energy, the wind holes will negate a potential hazard. Wind pushes hard on the side of any super tall structure, and in extreme weather, this same energy can cause vortices to develop on the opposite side of the building, pushing back the other way. These opposing forces can build up so much that the building begins to sway. But on Pearl River, the wind holes act as pressure relief vents, reducing the pressure on the building by about 1/3.
And in a super tall building, that's a tremendous amount of reduction because it helps to reduce the acceleration of the building and make the building more stable.
By reducing pressure, the wind holes not only make the tower stronger, but there are cost savings too.
So we need less steel and we need less concrete to help the building stand up, and that, of course, is a very sustainable thing to do.
It's also sustainable to harness the power of the sun. Photovoltaic panels will cover most of the east and west sides of the tower and the domed roof. Photovoltaic, or PV panels, take light energy from the sun and convert it directly into electricity, which feeds straight into the building's power grid. And the building will also capture energy from within. 29 of the tower's 31 lifts are fitted with a new technology called the regen drive, which recycles up to 75% of a lift's power consumption. Regen captures energy whenever a full lift travels down or an empty lift travels up, feeding it back into the building's power grid. On the 35th story, crews prepare to concrete the floor. And once again, innovation is saving time and money. On another super tall, this work could take 6 days, but here they do it in 3, thanks to the design of the floor plates.
This kind of floor was first seen in Europe. We've taken the idea and reinvented it.
Trusses are welded to the floor plates at the factory. The trusses reinforce the floor, so it needs far less reinforcing bar, or rebar.
This saves a lot of man hours and materials. When we're wire lashing the rebar, we only have half the workload. So it makes the construction very fast and very efficient. And the cost isn't higher than a conventional floor.
As the tower approaches 200 meters, 2/3 of its height, the danger of falling objects increases. On floor 45, Xiang Shangchai's team lays out safety nets. Worldwide, construction workers are 3 times more likely to be killed than workers in other occupations. Somewhere in the world, 1 worker dies every 10 minutes. That's 60,000 each year.
Sometimes small objects have fallen, but the safety net caught them. On this construction site, it's safety first. The life of the builders takes first place.
Through the brief Guangzhou winter, the tower climbs to 309 meters. For the first time, engineer Roger Frechette and architect Russell Gilchrist see the tower with glass installed.
No, you're not really, because the bit that will be visible. Seeing the building skin on and seeing the very graceful curves, both in plan and in section. I mean, just look up at the building beyond you. It looks fantastic. It looks amazing.
You know, you look up, it's breathtaking. The building looks like it's coming at you.
6,000 glass panels make up the building's outer skin. Just getting each panel from the ground and into place is a mammoth task. On floor 53, a crack team from the Zhanghe Curtain Wall Company fits the temporary rails they'll use to suspend individual glass panels and move them into place up to 17 stories below. This rail system will enable them to install all the windows from floors 36 to 52. Each rail weighs a hefty 100 kilograms. A hoist above suspends the rail until it's bolted in place. Down below, the glass team prepares to hoist windows to floor 36. Once the panels reach their destination, an elaborate system of pulleys and rails moves them across to the other side of the building.
The pressure is definitely here. The higher we go, the tougher it gets to install the facade. The challenge with this big building is that each panel is pretty big and pretty heavy. It's very difficult to move them.
With military precision, they lift each 400-kilogram panel to the open void, where it's attached via cable to the window rail above. At this level, wind heightens the challenge.
Because we're quite high, the wind is stronger when we lift them. We have to prevent them from crashing.
In a superb effort of coordination, workers on multiple levels guide the window along the side of the building.
Something that appears straight to the naked eye may not be. That's why we have to survey every panel we install.
In a building with multiple curves, where everything is calculated in 3 dimensions, no window can deviate from the master plan by more than a fraction of a millimeter. Before securing the window, a team seals the frame, a simple but crucial step in this tropical environment. Any gaps and moisture will get in. On average, the team installs 40 window panels every day. The steel skeleton is all but complete. Now crews are assembling the last of the main steel structures. These pieces will make up one of 8 steel arches that form the domed roof, the crowning glory of the tower. Assembling this giant jigsaw puzzle takes patience. This arch stands 18 meters high and weighs well over 20 tons.
Looking at this piece of steel behind me, it looks like it's probably about 20 tons, and they'll be lifting it up in the next day or so. I don't want to be standing right here when they do that. I'm going to be standing much further away.
In the race to complete the tower, the glass is being installed before the steel structure is complete. They've saved valuable time, but now this giant arch will pass perilously close to the building's fragile outer skin. The arches are some of the largest steel elements on the tower, and their installation signifies the beginning of the end.
We've entered the final phase of building. For every builder, a time like this is an exciting one. Because after a long journey of hard work, it's a time of fruition and victory.
They hoist the arch at a careful rate of 30 meters per minute, a nerve-wracking 10-minute journey to the top.
Coordinating between the steel structure and the glass facade is the most important task on this site. Most importantly, we need to pay attention to the wind. If the wind is stronger than level 4, then we can't do the job.
Today, the wind is approaching 14 kilometers an hour, just below that limit. Halfway up, the arch swings within 2 meters of the facade. Nature threatens to cancel the lift, but not because of the wind. Fog has engulfed the top floor. The crane driver is steering almost blind. Worse still, the work platform isn't ready. The floor team is behind schedule, leaving a hazardous work zone for the team that positions the arches. The fog closes in. Then, moments from aborting the lift, they manage to maneuver this 22-ton horseshoe deftly into place. Mission accomplished. From floor 68, Roger and Russell view the final phase. For both men, installing the arches caps a dream 5 years in the making.
The big arch, straight through the top, can you see it?
Yep, I see it.
That's just been bolted into place.
To see it here today in concrete and steel, and having reached the top of the building, 309 meters, it really is satisfying to watch it come together and become a reality.
Well, it is quite a thrill for architects and engineers seeing their work built. It's a very powerful image.
2 weeks later, they celebrate their success. On closed-circuit television, they watch as the very last beam is lowered in place. But one ambitious component will never be installed. The designers aspired to make the Pearl River Tower a net zero energy building, one that produces as much energy as it uses.
We set a very high mark at the very beginning of the project, net zero energy. This is the holy grail for mechanical engineers to have a building that contributes more than it consumes.
The architects hoped to reach their goal by harnessing the sun and wind, but they needed a third source of power. Their blueprints called for a fleet of 50 micro-turbines in the basement. These gas-fueled turbines would provide 3 megawatts of energy to the building during the day, and at night they would sell excess power back to the local grid in a process known as net metering. But the blueprints get snagged in red tape.
The city of Guangzhou currently does not allow net metering of commercial buildings.
Unable to sell power back to the grid, the designers can't justify the cost of the 50 microturbines. Out they go, along with the net zero dream.
There are certain things that won't allow Pearl to get to zero. But I think the true success of Pearl River Tower is the fact that it has opened this door and questioned, why not?
But we did take the first step. The first step that's going to encourage further improvement of energy-saving technology in the future.
And what better place to take that step than China? China has one of the fastest growing economies in the world, making it the second largest consumer of energy on the planet. It's the world's biggest producer of coal, which provides 75% of China's electricity. To keep up with demand, they add another coal-fired power plant every week. China has now surpassed the USA as the world's largest emitter of carbon dioxide. But most of that carbon dioxide doesn't come from the usual suspects.
A lot of people don't realize that buildings have more of a negative effect on the climate than automobiles or factories.
In fact, the world's buildings consume up to 40% of all energy. The Pearl River Tower looks beyond fossil fuels towards a greener future. For those who built it, the experience has been life-changing.
In my whole career, this project has given me the biggest pressure. I hope with a happy ending, my hair can turn black again.
When complete, the Pearl River Tower will be the most energy-efficient super tall structure in the world, and a benchmark for every designer to surpass.
This will be the very first time that wind turbines have been integrated into the very body of a building. This will be the largest water-cooled building in the world. It will be the largest double-skin facade building in the world, and of course the most energy efficient.
When you do something pioneering, it's not necessarily about that particular moment in time being successful, but the beginning of an idea. And if someone else takes what we have done and improves on it, nothing would make me happier.
We need a building that can be tested and monitored so that we can see how it's performing from year to year. Pearl River will give us that tool. And 50 years from now, they'll look at that building and say, this started the measurement system, this started the way forward in high-performance buildings.
The highest tribute to this tower of the future will come when it's a thing of the past.